In section 2.2, we're going to talk about inverse matrix. And also in section 2.3, we will continue to talk about the inverse matrix, okay? So before we get started, let's first define what an inverse matrix is. So let me give you the definition. So we're going to go, let A be a square n by n matrix. So this is important. Square means the number of rows and the number of columns are the same. So we can only find inverses of matrices that are square, okay? Let A be a square matrix, okay? If there exists, okay, a n by n matrix C. So there's another n by n matrix C such that, so here's an important thing to note here, exists. What that's saying now is that not every matrix has an inverse, okay? Some matrices do and some don't, okay? So if there exists a matrix, n by n matrix C, such that A times C, if you multiply A and C, we learned how to multiply matrices in the last section, you end up with an identity, okay? This is an identity that's n by n, that's what that means. And if you also reverse the order of multiplication, you take C times A, you still get the identity. Now, in the last section, we learned that if you multiply A times B, that's not necessarily equal to B times A, okay? But in this situation, A times C is the identity matrix, and so is C times A the identity matrix. When you have a matrix, when you find a matrix C that is special like that, that when you multiply by A, you get the identity, and it doesn't matter what order you multiply in, then that matrix C is a special matrix, okay? And we will call it the inverse. So let me go to write that down. Then A is invertible. That means we can find its inverse. That's what invertible means, okay? Or it's also referred to as non-singular. Non-singular means you can find the inverse of that matrix, okay? Then A is invertible, and C is called the inverse of A. Denoted by A with the -1 as an exponent, okay? So what does that mean? Let's write that down. So, okay, so C, out here we're replacing C with A inverse. So A times A inverse, okay, is equal to I sub n, and A inverse times A is also equal to that. That is C is equal to A inverse. Okay, so this matrix C that we had in the definition was a special matrix because when we multiplied A by that, we got the identity, and it didn't matter what order we did in. So because it is a special matrix, it's called the inverse of A. And we also say, because we can find that C, we say A is invertible. That means there exists an inverse of that matrix. And again, I want to stress this, not every matrix has an inverse. And we denote that C matrix by A raised to -1, okay? Now note here, this is A raised to -1 is not the same as 1 over A, okay? So that is not true, so please don't do that with matrices, okay? All right, so that is a definition of a inverse matrix. So the next thing we're going to talk about right away is a theorem associated with that. We're actually going to talk about many theorems, and I'm losing track of which number theorem it is, so I'm not going to give it a number. I'm just going to write down the theorem. So we're going to say that if A is invertible, okay, that means A has an inverse, okay? So A has an inverse. So if A is invertible, another word for invertible was what? What did we call it earlier? We called it non-singular, okay? If A is invertible, then it has only one inverse. I'll capitalize the word one inverse. So the inverse is unique in essence, okay? So what this is saying is that the inverse is unique. That is, inverse is unique. Can't have two inverses for the same matrix, okay? So that's what that means. All right, so if you want to see the proof of this, it's worth looking at it. It's fairly simple. It's a good, simple proofs, okay? So we're gonna, anytime you want to prove uniqueness theorem, you always start with two things because uniqueness means what, there's only one, right? So you start with two that satisfy the condition of the theorem. And then you, at the end, you show that those two are exactly the same. So in essence, we only have one, okay? So we're gonna start with two. We're gonna go let B and C be two inverses of A, okay? Then because they're inverses of A, what do we know then? We know that B times A is equal to I, and A times B is also equal to I, okay? And we know that C times A is equal to I, and A times C is also equal to I, because that is the definition of inverse, okay? Hence, okay, we can go ahead and multiply B. I'm going to do this. I'm going to say B is equal to, remember, my goal is what? To show B is equal to C. That means there's only one inverse, even though I started by saying there's two inverse. That's how we always do uniqueness theorems. Okay? So I'm going to start with this. B is equal to, if you recall from the last section, if you multiply a matrix by the identity, you're really not doing anything. It's like multiplying by one. So like 2 is equal to 2 times 1. You're not really doing anything. So B is equal to BI. These two are exactly the same. Is equal to, now this I can replace I with either this or I can replace it with this. It doesn't matter. They're both the same. So I'll replace it with AC. So I can write B AC. Okay. But wait a minute, what is BA? BA is right here. BA is also equal to I. So I can replace that BA with I. So I get IC. And what did we just say? When you multiply a matrix by an identity, you just get that matrix back. So we get C. So what did we just show? B is equal to C. And so therefore, B is equal to C. So we showed that the inverse is unique because we started with two different inverses and they ended up being the same. So we just manipulated some simple matrix multiplication and used the fact that when you multiply a matrix by an identity, you just get that matrix back. Okay? And then we replace this identity. We could have replaced it with either one, but this one works in our favor here because then I can replace BA. Had I used this one, then I would run into a problem. Like, for example, I would have had B times CA. That doesn't help me. And I can't rewrite this as C times B. I cannot do that. Okay, remember matrix multiplication, you can't move things around. Okay, hence we had to use this particular form, okay, or for I. So that's why we used AC. And then BA over here was equal to I. So we replace that in I times C. So these theorems are really easy to prove. They're kind of fun. Okay, so that was one theorem. The next theorem here we have, like I said, there's a whole bunch of theorems associated with inverses. I don't know if I'll prove all of them, but the uniqueness one was neat because there is a special technique to proving them. This one states that if A is invertible, that means it has an inverse, okay? Then A inverse is also invertible. So if A is invertible, then A inverse is also invertible, and A inverse inverse is actually equal to A. Okay, so let's see if we can prove this one. Again, like I said, these are really nice proofs to do. They're straightforward. Okay, So we know that A is invertible. So we'll start with that. That was our assumption here. So we're going to start with since A is invertible. So right away we can use the definition and say, since A is invertible, we have A times A inverse is equal to I, and A inverse times A is equal to I. Okay. So, but we know that A inverse is also invertible. Okay. So what does this mean? Let's just take a look at just this piece for a second. That means we learned that if A is invertible, then the inverse of A was this, correct? If A was invertible, then the inverse of A was this. Or you can say if A is invertible, the inverse of this is this. But wait a minute, we also know from this, we can also say what? This is invertible, correct? Because if I multiply this by A, I get identity. If I multiply this by A, I get identity. So what does that mean? That means that A inverse is also invertible, okay? Because anytime you multiply two matrices and you get identity in either order, then they are inverses of each other. So this implies that A is invertible. So hence A inverse, sorry. Hence A inverse is invertible. Okay, so A inverse is invertible. Thus, okay, A. So from here, so like I said, out here I showed you that if A is invertible, then the inverse of A is this. Why is that? Because whatever you multiply by and you get an I in any order, the other one becomes the inverse of that matrix, right? But we can also see from this that A inverse is invertible, and the inverse of that is this, correct? The inverse of this would be that then. Okay, so that tells me that, and since A inverse is invertible, thus A is the inverse of A inverse. Okay, therefore A inverse inverse, so the inverse of this is A. So A inverse inverse is A. And that's how we get that. Okay, all right. So if A is invertible, the inverse is also invertible. Okay. The next theorem that we're going to talk about here, like I said, many theorems here, is this. If A and B are invertible, are n by n invertible matrices, so I have two matrices that are invertible, then the product is also invertible. So that is interesting. If you have two invertible matrices and if you multiply them, then the product you end up with will also be invertible. And the inverse of that, so this is interesting. This is very similar to the transpose. The inverse of this is given by B inverse, A inverse. Look at the order here. It's different, okay? So if A is invertible, then the inverse of that is also invertible. All right, so let's check this. So we have to show two things. We have to show that AB is invertible. If A and B are invertible, then we want to show AB is invertible. And then we also want to show that the inverse of that AB looks like this, okay? So it's like a two-part proof. We have to prove two things. So let's start with the first one, okay? So to show that AB is invertible, what do we have to show? What is the definition of invertible? There's some matrix A that when you multiply, you get I, and then when you flip the direction and multiply, you still get I, correct? So we're going to start with that. So we are saying that, okay, so we have AB times, we have B inverse, A inverse. Now, why am I using that? Because we know that if this is invertible, then the inverse looks like this, right? We just showed that. So if I can multiply these two and end up with I, and I can switch it and do the same thing, reverse it and do the same thing and still get I, what does that tell us? That the inverse of AB must be this, correct? That's what it would imply, okay? So we're going to do that. So let's start with that. So the first thing I need to show is this is I. All right. So I'm going to use the associative property. So I'll take, instead of multiplying these two, I'll multiply the middle two first. I'm not changing the order of multiplication. I'm just changing which two am I multiplying. That was a property from the last section on product. And since B is invertible, if you multiply B times B inverse, you should get identity, correct? So we'll get A times I, A inverse. And when you multiply any matrix by an identity, you just get that matrix back. So you get A times A inverse. And since A is invertible, A times A inverse must be I. So we just showed that this is equal to I, and we also want to flip it and do the other direction. So we're going to do the same thing. We're going to change the order in which we multiply, we're going to change which two we multiply first. We're not changing the order, okay? So get that. Since A is invertible, A times A inverse is I. Okay. Anytime you multiply a matrix and an identity, you just get the matrix back. So we get this. And since B is invertible, B inverse times B must be. So when we multiplied these two matrices, we got identity in both cases. What does that tell us? That these two are inverses of each other. You guys follow? So if I take the inverse of AB, I should get this, okay? So that's what that implies. So we can say hence, first of all, because we get I in both cases, we know that AB is invertible. Hence, AB is invertible. And AB inverse, if you would take the inverse of that, is going to give you B inverse, A inverse. Okay, and we'll end up with that. Okay, so that was another theorem associated with inverses, but this is important to remember because there's a whole bunch of homework problems where you have to use this fact, okay? And remember, when we take the inverse of a product, the order changes in which you do the product, then you get B inverse, A inverse, not A inverse, B inverse, okay? The next theorem has to do with transpose. Okay. And again, I'm doing these proofs because they're so simple and they're just using the definition in essence, okay, of an inverse. If A is invertible, then A transpose, okay, is invertible. Okay. And the inverse of A transpose is equal to A inverse transpose. So keep an eye on how those exponents are getting moved around. Okay. So we are saying that if A is invertible, then so is A transpose. Okay, so what we want to show to start with is we want to show that if I take, I'm sorry, if I take A transpose and some matrix, I don't know what that is, I'll tell you what it is, and end up with I, and if I take that same matrix here and take A transpose and still end up with I, then the inverse of this is this. You guys follow? Or the inverse of this is this. Is that okay? All right. But in essence, they told us what that missing matrix is. It's right here. Because they've told us that the inverse of this, you can see that inverse of this is actually this. So to do the proof, we'll do what we did in the last proof. We'll take A transpose times A inverse transpose, because we know that the inverse is given by that, right? So we want to show that if I multiply these two, I get an identity. So let's see if we do. Okay. If you recall from the property of inverses, if you take A times B, I'm sorry, not transpose. If you take A times B transpose, we get B transpose A transpose from the last section. So if you have this, I can write it this way. If I have this, I can write it this way. I have this form right now. I have this and this. So if I want to write it as a product transpose, then I'll have to switch the order. So I'll get A inverse A transpose, A transpose. Okay, so that's what we'll get. Okay. So now where can we go from here? Okay. Just a second. Okay. We get, oh, sorry. We don't have the transpose on the inside. Got an extra transpose because these two transpose become a single transpose, okay? We have that. We know that A is invertible, so A inverse times A will be I transpose. And the transpose of an identity, if you think about an identity, let's say a 3x3 identity, if I take the transpose of this, you'll literally get the same thing again. So transpose of an identity is just the identity. So in this case, we'll just get I. So when I multiplied these two, I got I. So that tells me maybe the inverse of this is this. Is that okay? But I still also need to do the other direction, okay? You need to do both. So let's start with that. And now I'll flip it around. A inverse transpose A transpose. I want to show that that is also I. We can use the same property of transpose and write it as 1. We get this. The inside is an identity. So we get I. So in both cases, we got I. So that tells us, hence, we can say what? A transpose is invertible, because if you multiply A transpose by the same matrix in any order, we get I. That means that is invertible. So we can say, hence, A transpose is invertible. That was one of the things we had to prove. And the inverse of A transpose will be whatever this is. In this case, it's what? A inverse transpose. Okay? And that was the second part we had to show. So once again, I'm hoping you understand how to do these simple proofs. They're kind of fun. Okay? And just so you know, this can be extended to products of more than 2 matrices. Okay, so let me put that down as a note. So note that if I have a matrix A1 times A2 times A3 dot 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 AN, I have n matrices. I'm sorry. I'm talking about this theorem. I apologize. This one. Okay. This one applies to a product of 2 matrices. We can, if you take the product and then the inverse of that, you can take the inverse of each individual matrix in the opposite order. So, but we can apply this theorem to a whole bunch of matrices because that's going to be important to us. So, but the only thing is the whole order will flip. So you'll get AN inverse, okay, dot, 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 A3 inverse, A2 inverse, and A1 inverse. So if you have a whole bunch of matrices and you're multiplying and you're taking the inverse of that, you'll just flip it and get the same thing, okay? All right. That brings us to the next theorem on inverses. Actually, you know what? I'm going to label these theorems because this is a new chapter, so we can label them accordingly, okay? So I'll call this theorem 1. This will be 2. That's a good idea to number them so we know which one's which. 3 and 4. Okay, so now I'll do theorem 5. So theorem 5 states that, this is a nice theorem, so this is an important theorem, so let me put a star next to it. It states that if A is an invertible, that means it has an inverse, invertible n by n matrix, okay, then for each B, vector B in Rn, not just a specific one, for every B in Rn, okay, the equation Ax equal to B, okay, has an unique solution. So you've guaranteed a unique solution if A is invertible, okay, unique solution. And the solution is, not only do we get the unique solution, we know what it is. The solution is x bar, remember we're trying to find x, is equal to A inverse times B. So this theorem tells us that if you have an invertible matrix, then you're always guaranteed a solution for every vector B in Rn, which is really neat. Okay, not just one specific, but you're always guaranteed a unique solution, not infinite solutions or no solutions, unique solution. And that solution is given by this vector. So let's take a look at the proof of this. Again, a very simple proof. So we're given Ax is equal to B. This is the equation we are trying to solve, correct? For some B in R. I'm sorry, not some. For each B in Rn. Okay, that's for every B in Rn. Now, I'm going to multiply both sides by A inverse because A is invertible. I can find its inverse. So I'm going to multiply both sides by that. Okay. We know that A inverse times A, because A is invertible, if you multiply the inverse and the matrix itself, you get I. And if you multiply any matrix by a vector or if you multiply an identity by a vector and identity by a matrix, you just get that vector or that matrix back. So in this case, we get X is equal to A inverse B. Okay, so there's my solution. Okay, we got the solution, but wait a minute. We still need to prove uniqueness. We need to prove that this is the only solution. Okay, how do we prove uniqueness? Remember, what did we do? We always start with two solutions and then show that we have only one. Okay, so we already know X is a solution here. So we know, let me write that down. We know X is equal to A inverse B is a solution. We already know that, correct? So now we're going to pick another solution. We're going to go let U be another solution of A X is equal to B. Okay, so what does that mean? That is AU is equal to B because we're saying U is another solution. So if I replace X with U, I get that. Okay, all right. So let's start with that. So we can go thus. We have AU is equal to B. I'm going to multiply both sides by the inverse again. I can legally do that since A is invertible. Okay, this is equal to I. And this from here is equal to X. We know that. So if you multiply X by U, we just get U. I'm sorry, if you multiply I by U, we just get U. And then we get X. So we showed U and X are the same. So we had one solution. Now we started with another solution. Okay. And we wanted to show in uniqueness. If you have two solutions, we always want to show they're exactly the same. And that's what that implies uniqueness. So we just implied uniqueness. Hence the solution is unique. Okay. So we had to show two things. We had to show that the solution is unique, and we also had to show what the solution is. So we started by first showing what that solution is, and then we showed uniqueness. Okay. All right. So there's a lot of theorems there. We have done 5 theorems. There's more to come. But before we do any more theorems, let's switch gears and talk about something really cool. Okay. So we're going to talk about this concept of something called elementary matrices. We're going to talk about this idea of, we're going to talk about the special matrices called elementary matrices. So let me give you a definition of it. So an elementary matrix okay, we'll denote it by EM, so I don't have to keep writing elementary matrix all the time. An elementary matrix is obtained by performing and I'll capitalize this word one and underline it, by performing one row operation on an identity matrix. So this is really cool. Okay. What this is saying is that to get an elementary matrix, you start with an identity matrix and you perform one single row operation. Now, what are row operations? We have three types of row operations, correct? We have scalar multiplication, we have row swap, and we have row addition. You remember that from section 1.1. So there's only three types of row operations. So if you apply any one of these row operations to the identity matrix, then what you end up with is called the elementary matrix. Okay, so let me give you some examples. All right, so here's one. I'll do an example of each of these. Okay? So let's start with this one. So I'm going to start with an identity. Okay, I'm going to do it with a 2x2 matrix. Okay, you can do this with a 3x3, 4x4, 5x5. It doesn't matter. It's just easier to work with 2x2. So if I take the identity matrix I2, which is this 1, 0, 0, 1, and I perform one single row operation, I'm going to start with scalar multiplication, okay? So what does that mean? I'm going to pick any row, doesn't matter which one, okay? So I'm going to take the second row and multiply it by some scalar k, okay? So I'm going to take k times R2 will give us a new R2. So if I do that, I'll end up with this new matrix. And then this new matrix is going to look like this. The first row stays the same. The second row becomes 0k, right? And this is called an elementary matrix. Okay, that's one type of elementary matrix. Okay, so, and there's a lot of notation. Sometimes they'll write it this way. They'll go E parentheses K2. That tells us that you multiplied row 2 by K. That's what that means. Okay. Here's another example of row swap. So if you have a 2x2 identity matrix, and look at that, we only applied one row operation, 0, 0, 0, 1. If you want to swap two rows, we write R1 with arrows on both sides, R2, correct? So then we'll end up with 0, 1, 1, 0. That's what will happen to the identity. And so this is another elementary matrix. Now this one, we write it this way. We just put E1, comma 2. That means you swapped the first and the second row. That's what that means, okay? Those are just notation. Not everybody uses these notations, okay? I'm just giving you, just in case you ever come across some, you'll know what they mean, okay? And then the last one is row addition. So let's say if you again start with an identity. So you can see in all three cases, we're applying one single row operation, scalar multiplication, row swap. And now we're going to do a row addition. So I get K times R1 plus R2 gives us an R2. So we're changing R2. So we get 1, 0, K1. So this is another elementary matrix. And some of you might go, wait a minute, that's row addition and scalar multiplication, but this is technically considered as one operation, okay? So in this case, we would write it this way. We would go E parentheses K1, we're multiplying row 1 by K, and then we'll put plus 2. That means you're adding it to row 2, okay? And so it's, again, don't focus so much on the notation, just understand what an elementary matrix is. It is just starting with an identity and performing a single row operation, okay? All right, so here's a cool, well, let me write a note down first. Let's see, note, okay? Row operations. So here's the cool thing about elementary matrices, okay? Row operations on matrix A. And by the way, the only reason why we're studying this is this is what's used in theory to prove some theorems, okay? This idea of elementary matrices are used for proving. Other than that, they don't have any computational value, okay? Row operations on matrix A can be represented by EA So a row operation on a matrix A, so if you perform some row operation, one of these row operations that I listed up here can be represented by EA, okay, where E is created by performing the same row operation on I, the same row operation on I. So E is an elementary matrix, okay? Because to get E, we perform one row operation on I and we get E, right? So instead of performing the row operation on A, we perform that row operation on I and create E and then use that and multiply A by E, and that'll result in the same thing as if you were performing that same operation on A. Again, computational wise, this makes no sense. But again, this stuff is used for proving theorems and things like that and theoretical stuff, okay? So let me give you an example of this just to show you, okay? So I'll just do one example just to show you. So let's say that if you multiply by a scalar, okay? So if you take some, we have some matrix A, and I'll just call it, it's got numbers A, B, C, and D. These are just some numbers. So if I multiply the first row by some scalar K, so we get K times R1, gives us a new R1. So A becomes what now? A will look like this. We get KA, KB, C, and D. Okay, that's great. Now let's try to do that using this note. Okay, so what we can do first is create E. Okay, what is E going to be? E would be where you perform the same row operation on identity, right? So what row operation did we perform here? We multiplied the first row by K. What does that look like? Out here, I give you an example of multiplying the second row by K. Had I done the first row, this would become a K and this would become a 1. So this would be my elementary matrix, okay, for that. So I'm going to say E is equal to K0, 0, 1. That corresponds to this row operation. Is that okay? All right. So now, according to, let me actually write down a little better words. It's just, I'm going to just write it. So the elementary matrix for the above row operation is E is equal to K001. Okay, now that note told us that instead of applying the row operation on A directly, we can apply it on E and then multiply E by A. Okay, so E times A plus E times A should give us this, right? So let's see. So I'm going to start with E, which is 0, K001, and then A was A, B, C, D. So we're going to do row times column. Row times column, I get KA. Row times column, I get KB, because when you take 0 times C, you'll get 0, and 0 times D will give you 0. Okay. Row times column, 0 times A is 0, 1 times C is C. Row times column, 0 times B is 0, and 1 times D is D, which is exactly the same as this. So, like I said, computationally, this makes no sense, but for proving theorems, this is very practical. Okay. So instead of performing the row operations on A, we're going to perform it on, we're going to create the elementary matrix for that particular row operation, and then multiply the given matrix by the elementary matrix to give you the same result. Okay. All right. So that's kind of neat. The second note, so that's note 1, I should really say 1. Okay. Note 2 here is that elementary matrices are invertible. Elementary matrices are invertible. That's cool. We can find the inverse of those, okay? The inverse of E is another elementary matrix. So is the elementary matrix okay, that transforms e to I, e back to I. So if you have an elementary matrix, to find its inverse, you have to just perform another row. You have to find another elementary matrix that'll change that e back to I. So let me give you an example of that. Okay. So here's an example of that. So let's say that we have, we'll just do the scalar multiplication. Well, let's do something different. Yeah. So let's say that I have this elementary matrix. E is equal to 1, 0, K, 1. So this is an elementary matrix, okay? The first thing I need to do is to find the inverse of this. I have to ask myself, what row operation, okay, will change this back to an identity? Do you follow? So to do that, what are we going to do? We're going to multiply the first row by negative K and add it to the second row, correct? And that'll change it back to identity. So the inverse of this matrix will be, you're going to perform the row operations. What did we perform here? Like I said, you take negative K times R1 and add it to R2, which will give us a new R2. Okay, so let's do that. So if I do that, what do I get? Okay. Oh, I want to find the elementary matrix. So remember, to find the elementary matrix, what are we going to do? We're going to start with an identity and perform this operation, okay? So remember that. We're not performing the row operation on this. We are performing, to get the, what is elementary matrix? You start with an identity, perform a row operation, and you get an elementary, correct? So in this case, we're going to perform this matrix, we're going to perform this row operation, because this row operation will change this to an identity. So we're going to perform it on this. So we get 1, 0, negative K, 1. Okay, so this is the inverse of this matrix. Okay, so we started with some elementary matrix, and then to find the inverse of that, we asked ourselves, what row operation would we perform on this one to change it to I? Okay, so we knew which one we would perform. So once we know that, then you start with an identity, perform that row operation, and that'll give you a new elementary matrix, and that'll actually be the inverse of the one you started with. Okay, so let's check it. So let's go ahead and check it. To check it, what do we do? You can multiply them and see if you get I, correct? If they're inverses of each other, E times E inverse should give you I, correct? So let's check. So E is 1, 0, K, 1, and E inverse is 1, 0, negative K, 1. Okay. Remember, this should give us I if they're inverses of each other. So row times column, 1 times 1 is 1, 0 times negative K is 0, row times column, 1 times 0 is 0, 0 times 1 is 0, row times column, 1 times row times column, 1 times K is K, and 1 times negative K is negative K. K minus K is 0. Row times column, we get 1. So we get the identity. So that tells me that these are inverses of each other. Okay, so that's important there. Okay. All right. The next theorem we're going to talk about, this is theorem 6. Okay, which states that this is a very important theorem. Okay, out of all the ones we've done there, this is by far the most important, because so far we know what an inverse is, but we don't know how to find it. We know what it is, but we just don't know how to find it. So let's take a look at it. Okay, so we have a n by n matrix A is invertible. That means we can find its inverse if and only if it is row equivalent to I n. What that means is, if you remember, row equivalent means what? I can perform row operations on A and convert that to I. Okay, I can perform row operations on A and change it to I. So it's I and any sequence of row operations, okay, that reduces A to In to I also transforms In into I inverse. So now we have a game plan or a blueprint on how to find the inverse. So far, we just knew what an inverse was, but now this theorem actually gives us a blueprint on how to do that. It's saying that what this theorem is saying is, in a nutshell, what it's saying is, if you start with a matrix A, okay, and you perform row operations, okay, and you change it to In. Okay, so as you're doing this, as you're performing row operations and changing it, then at the same time as you're doing this step, as you're doing step one, step two, along the same time, you start with an I and perform the same row operations that you performed here. So I'm going to use a different color just to illustrate that. These row operations that you perform on A, you're going to perform the exact same row operations on I. And you're going to end up with a new matrix. That new matrix that you're going to end up with is actually going to be the inverse, A inverse. Is that okay? So the same row operations that you perform on A to change A to I, because A is row equivalent to I, you can perform those exact same operations on I, and that'll change that I to a new matrix, and that new matrix is going to end up being the inverse of A. Okay, so that's what that theorem is telling us. So it's a really cool theorem because it's actually giving us a blueprint on how to find the inverse. Do you follow? So it's giving us a nice blueprint on how to find that inverse. Okay, so let's take a look at that. Okay, so I'm going to do an example on how to do this. So let's start with, um, let's see, okay. So let's do an example. I'm going to start with a 3 by 3 matrix and see if we can row reduce it. Okay, so we're going to go, we have this matrix 1, 2, what's 1, 0, 1, 3, 2, 1, 4. Okay. All right, just give me a second. So we get 4 minus 3, and then you get plus 2 times 6 minus 1. So that gives us 1 plus 10. So that gives us 11. Okay. So this is invertible. Okay. All right. So how do you find the inverse? So what are we going to do? We're going to try to find the inverse of this matrix. Okay. We're going to perform row operations to change this to I3 because it's a 3 by 3. And we're going on the side, we're going to do the same thing, start with an I3 and perform the same row operations. And we're going to end up with this new matrix, which is going to be the A inverse. Okay, so the same row operations we're going to perform here. So the best way to do this is just do them side by side. Okay, so I'm going to start the way they do that. The way you denote it is you start with this 1, 2, 3, 0, 1, 3, 2, 1, 4, 1, 0, 0, 0, 1, 0, 0, 0, 1. So we are starting with this here and we are starting with this here. So whatever row operations you perform to change this to an I, we're going to perform the same row operations on this side too. Okay, so let's do that. So the first thing I'm going to do is make this to a 0 because I want to change it to an identity. An identity, 3 by 3 identity looks like what? It looks like basically this. You're roughing it in essence. Do you follow? So I'm going to take -2 times row 1, add it to row 3, which will give us a new row 3. Okay, so let's do that. We have the first 2 rows are unchanged in both the matrices. Okay. So we get 0, 1, 3, 0, 1, 0. This becomes a 0. 2 times -2 is -4. -4 plus 1 is -3. 1 times -2 is -2. -2 plus 4 is 2. 1 times -2 is -2 plus 0 is -2. 0, 1. Okay. Now we want to get a 1 on the diagonal, which we already have, because once you're done with the column, you go to the next column, get the 1 on the diagonal, and use that to make everything in that column 0. So I'm going to multiply this 1 by -2 and add it to this, and this 1 by 3 and add it to this, okay? So we get -2 times row 2, add that to row 1, which will give us a new row 1, and 3 times row 2, add that to row 3, and that'll give us a new row 3, okay? So 0 times something is 0, add that to 1, just gives us a 1. 1 times -2 is -2 plus 2 is 0. 3 times -2 is -6. -6 plus 1, okay, is -5. 0 times something is that, just gives us 1 times -2 is -2 plus 0 is -2, 0. The second row stays the same because we didn't change that. Now we're going to multiply by 3. So we get 0. 3 times 3 is 9. 9 plus 2 is 11. So this gives us -2. 1 times 3 is 3. So we get 3 and a 1. Okay. Now we want to make this into a 1 because we are done with the second column. We go to the next column. So I'm going to divide R3 by 11, and that is going to give us a new R3. Okay. Scalar multiplication. The first two rows are not affected. So we get 0, 1, 3, 0, 1, 0, 0, 0, 1, divide by 11, -2 over 11, 3 over 11, and 1 over 11. Now we're just going to use that 1 to make everything in that column 0, and then whatever is left is going to be an inverse. I'm going to multiply this by 5 and add it to this, and -3 and add it to that. So you get 5 times R3 plus R1 gives us a new R1. -3 times R3 plus R2 gives us a new R2. Okay. So we get 1, 0, 0. We're going to multiply, that's just 0, so it doesn't multiply this by by 5. I'm sorry. Multiply, oh, that's wrong. So what are we going to do? Multiply this by 5, row 3 by 5, and add it to row 1, right? So you get 1 minus 10 over 11 because you'll multiply by 5, so that -2 will become a -10 and add it to row 1. So you get 11 minus 10 is 1 over 11. 3 by, so you'll get 15 over 11 and add it to row 1, which is -2. So you'll get 22, -22. So you'll get -7 over 11. And then out here, we're going to multiply this by 5 over 11, 5 and add it to row 1. So you just get 5 over 11. So we get 0, 0, 1. Now this time we're going to multiply by -3, row 3. So -3 times 2 is 6, 6 over 11, and add it to row 2, which is 0. So you'll just get 6 over 11. We multiplied this by -3, so it'll be -9 over 11, and add it to the 1. Common denominator is 11, so you'll get 2 over 11, positive. And then we multiply this by -3 and add it to the 0, so you'll get -3 over 11. The third row stays the same. Oops, this is a 1 here and a 0 here, sorry. So we get -2 over 11, 3 over 11, and 1 over 11. So we transformed, look at it, we started with A, we transformed, I'll use 2 different colors to illustrate that. We started with A, and we transformed A to I. Okay, in the process, what happened? In the process, the I that we had here, the one we started with, got transformed to what? A inverse. So the inverse of this matrix A that was given to us is given by this. So A inverse is -1 over 11, -7 over 11, 5 over 11, 6 over 11, 2 over 11, -3 over 11, minus 2 over 11, 3 over 11, and 1 over 11. So that is the inverse of the given matrix A. Now, if you wanted to check your answer, what could we do? We could basically multiply A and A inverse until we get an identity. Do you follow? Now, just to check it really quick, I'm not going to do that, but this is going to take time. I'm just going to use my calculator to do this instead. Okay? If you have a TI calculator or something, you can do this quickly. So I'll clear this. I'm going to go second and matrix here. I'm going to edit the first matrix. We'll make it a 3 by 3. Okay? So we have 1, 2, 1. And then the second row is 0, 1, 3. And then the last row is 2, 1, 4. Okay, so we got our matrix. So we're going to quit. We're going to go to second and matrix again. We're going to pick our first matrix and find the inverse of that. Okay, so let's do that. And we get that. We're going to change that to a fraction. So we get that. So let's see if that's correct to what we had. So my first row was 1, 11, 6 over 11, negative 2 over 11. My second row was negative 7 over 11, 2 over 11, 3 over 11, 5 over 11, negative 3. So that's correct. And like I said, you could multiply A and A inverse and show that you get I. So you can see how this theorem works. Okay. Right. Now, the last theorem that I'm going to give you out here. Okay. Let's see. So this is this is theorem 8. Okay. I think it's 8, right? No, it's 7. Sorry, my bad. It is theorem 7. Okay. So now this theorem is really interesting. It applies to a 2 by 2 matrix. Okay. So this gives you a shortcut on finding the inverse of a 2 by 2. It doesn't work for any other matrix, only 2 by 2. Okay. So it states like, it goes like this. Let A be the matrix A, B, C, D, where A, B, C, D are just some numbers. Okay. All right. So that's given to us. If, okay, AD minus BC is not 0. That means if you multiply these two and then if you multiply these two and then you subtract the product of those two, and that product is not 0, okay, then, okay, A is invertible. And not only is it invertible, the inverse of A is, I can actually find it. A inverse is going to be 1 over AD minus BC, that's this thing that we just found, times, you're going to swap the main diagonal. So this main diagonal you're going to swap, so you're going to get D and an A, and then you're going to multiply the other diagonal by a negative, minus B minus C. So not only can we know when this matrix is invertible. Remember I said at the very beginning, not every matrices are invertible. Okay, and not only can we know when this matrix has an inverse, we can actually find the inverse by using this formula. So we don't have to do this. This kind of gets tedious. Do you guys follow? So we don't have to do this. For 2 by 2, it's really simple. So let me give you an example just to show you how that works, okay? For a 2 by 2. Here's a quick example. So let's say we have A is equal to negative 1, 2, negative 3, 4. Okay. So the first thing we're going to do is, let's see that if you, actually, hold on. Let's change this a little bit. Let me change this. Let me use this now. Let's use 2, 4, 6, 8. 2, 4, 6, 8. Okay. This is a 2 by 2 matrix. Now, the question is this invertible? So the question is this, is A invertible? If it is, If it is, then find the inverse. Okay, so to find if it's invertible, we take the product of the main diagonal, okay, and subtract the product of the minor diagonal. Okay, so let's do that. So the first thing I'm going to do is take 2 times 8 minus 6 times 4. That gives us 16 minus 24. That gives us negative 8. This is not 0. So this implies A is invertible. So now we know A is invertible. Now that we know it's invertible, let's find the inverse of it. So A inverse is going to be 1 over this. Remember, this is like your A, B, C, and D. So you get 1 over B minus AD minus BC, which is negative 8. So you get 1 over negative 8, okay, times, you swap the main diagonal. So this becomes a 8 and a 2, and you multiply the minor diagonal by a 4, by a negative. Now this is like multiplying a matrix by a scalar. So you multiply everything by that scalar. So I'm going to do that. You always want to clean it up. Okay. So 8 multiplied by 1 over negative 8 will give you negative 1. Negative 4 multiplied by 1 over negative 8 will give you 1/2. Okay. Then negative 6 multiplied by 1 over negative 8 will give you 3 over 4. And this will give us negative 1 over 4. So this is the inverse of this matrix. So you can see how easy it is to find. You can do it really quickly. Okay. All right. Let's piggyback on that example. Let me ask you this. Solve the system AX is equal to B, where A is the same as in the last example, and B is, let's make up B. So let's say B is, should we make up for B? You can say B is, let's pick something easy, 1, 0. Okay, so we want to solve this system. We know how to do this. We can take AX. So one way to do this is we can take AX is equal to B, and we can write it as an augmented matrix, A slash B, and we ref it, correct? And that'll give us the answer, okay? But that's something we've been doing, but let's use the fact that from the previous example, we know A is invertible, and we actually found the inverse. So if you recall from theorem 5, we know that if AX is equal to B, this implies that X is equal to A inverse of B. That was theorem 5, okay? So let's use that fact. So I know A inverse from the previous example. We know it was, what was it? Minus 1/2. We had 3/4 and negative 1/4. Okay. And B was 1, 0. So we just have to multiply these two and we'll get the answer. So if you multiply these two, we get row times column, row times column. Negative 1 times 1 is negative 1. Half times 0 is 0. Row times column, we get negative 3/4 times 1 is negative 3/4, and negative 1/4 times 0 is 0. So there's X. There we go. We just did it. So we didn't have to ref it. Now, just so you know, refing, doing it. So the question is, which one is a better method? Well, out here, we first have to know the inverse. The only reason why we were able to do this quickly is because we found the inverse out here in the previous example. Okay, just so you know, refing is usually the better option. Always, it's faster on the computer. Okay, this one will take a lot more computer power, because you'll have to first find the A inverse, and then you'll have to do the multiplication. So that's a lot more work. Okay, all right. So I think that's about it in that section. I'll just end with just one quick note. I'll just end with this note. What if let's say that I'm interested in, just like in this example here, I don't want to find the whole matrix, whole inverse. Maybe I just want to find let's say this column, the second column. So A2 bar, we write that as a vector, right? This is A1 bar, A3 bar. So what if I just want to find one? Then I don't need to do all this unnecessary work. I can just find one very quickly using this fact, okay? One column. Okay, so let's see how to do that. So if we are interested only, let me capitalize the word only. If we are only interested in a single column of A inverse, okay, then we can do the following. Then we can do the following instead of finding A inverse. So if you're interested in only a single column, then we can do this. Okay, so here's what we can do. So we can say let A, this is A, not A inverse, be A1, A2, okay, dot, 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 AN. Okay, and A inverse is given by this. It's going to be X1, X2, dot, 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 Xn. Okay, so, all right. Since we know this, right? Since we know A times A inverse is going to give us what? An identity, right? That's the whole idea here, okay? So what can I do here? I can multiply A times A inverse, okay? So if I do that, if you recall from the last section, we can do right multiplication like this, the matrix times a vector, x1, that'll give us the first column. The matrix times a vector, x2 will give us a second column. The matrix times a vector xn will give us the next. So if you multiply these two matrices, that's just doing this, okay? This was the theoretical way to multiply two matrices. And on the right, we have E. Well, E is what? E1, E2, dot, 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 En. If you recall, each column of the identity is called the E1 vector, E2 vector, E3 vector. Each column has a label. Okay? All right. These two are exactly the same. So what does that tell us? This implies AX1 should equal to E1. AX2 should equal to E2. And so on. AXN should equal to En. Okay. So if we only want a particular column, okay, we just solve that system. These are systems, really. We have n systems. We don't want to solve all of them. That's tedious. But if you're only interested in one particular column, we just solve the system for that particular column. Okay. So let me write that down. So if we only want the second column, for example, okay, of A inverse, okay, we only need to solve the system AX2 is equal to E2. Okay. All right. So this will give us the inverse. This will give us the second column of A inverse. Okay. So that is just a trick, instead of finding the whole thing, if you just want to find one particular column, we can use this little trick. Okay. So let me just show you. I'll do it with a 2x2 really quick just to show you. Okay. If you recall, the 2x2 we started with was we had 2, 4, 6, 8, correct? Okay. So I want to find only, so we want to find the second column of A inverse. Now this is an easy thing to find. We actually found the inverse of this right here. So what is the second column of this? It's this guy, half and negative 1/4, okay? So that's what we want to find. So how do we do that? Well, to find the second column, we solve AX2 is equal to E2. Okay, so what does that mean? That means that we take the matrix A, which is 2, 4, 6, 8, and on the right-hand side, we put E2. E2 would be the second column of an identity, which in this case, since it's 2 by 2, it's a 2 by 2 matrix, it'll be 0 and 1. So we solve this system, we ref it. Okay, so we can ref the system. So I'm just going to quickly do that. I'm going to multiply the first row by -3 and add it to the second row. Okay, that'll give us row 2. So I get 2, 4, 0. We get 0. 4 times -3 is -12 plus 8 is -4. And 0 times that's just it. Now we're going to divide everything by -4, the second row by -4 to get that pivot. So we get 1 over -4 times R2 will give us a new R2. Okay. The first row stays the same. So we get 0, 1, -1/4. Okay. Now we're going to take 1 and add it to the first row. Okay. Or we can just do back substitution at this stage, okay, if you wanted to. So, okay. So I'm going to call these x1 and x2 because we're trying to find x1 and x2, because remember the inverse matrix columns, we call them x1, x2, x3. The regular matrix was a1, a2, a3, okay? So that tells me that x2 is equal to -1/4, which actually gels with what we had here. Right there was -1/4. Remember, we're looking for the second column, so we already know that. So x1 should be half. So let's see if we can get a half here. So the first row tells us what? The first row tells us 2x1 plus 4x2 is equal to 0. So we get 2x1 is equal to -4x2. So we get x1 is equal to -2x2. And then replace x2 with what we know. So we get x1 is equal to -2 times -1/4, because that's what x2 is. So we get 1/2, which is exactly what we wanted. So the second row of A inverse looks like this. Okay, so this is the second row. I'll put a bar because that's a vector. Looks like this. The first number is 1/2 and the second number is -1/4. So that's how that little note works. Okay. We didn't find the entire thing. I just did it for a small example to kind of drive home the point. Okay. All right. Just so you know, again, out here, I just want to leave with one thing. There's two ways to solve a system. You can either solve it this way by reffing, okay, or you can do it this way by taking A, if A is invertible. Okay? Now, this is always faster. Please remember that. Okay? It's always better. This is just another way to do something, the second method, but the first method is usually faster, usually 3 times faster than doing this one. Okay? Just so you know. All right.